Without further ado, let me start talking about our main speaker, who will be much more interesting than I am. John Spencer is a friend and colleague of mine, and we were both at the Southwest Research Institute, where John has been for the past 11 years. That's in Boulder, where he is one of the lead scientists, obviously, on the New Horizons project. But we could fill most of the year of our public night talks with John with all the different topics that he has researched. He is a specialist on the moon Enceladus, which is a very interesting moon of Saturn. He has worked on Uranus and Neptune data, and actually I was, as a very young early in my research career, part of the team for the Voyager flyby of Neptune. And John, before I knew him, was also out there, not only for Neptune, but the previous flybys of Uranus and Saturn. And just to share briefly with you, because this is going to be a part, I'm sure, of the Pluto encounter, there's just nothing like it when a satellite that we've built here has traveled out that far in the solar system. And New Horizons launched in, was it 2006? And we wait and wait for the better part of a decade, and it finally is arriving there, and you're just waiting for the first data to come in. I remember when I was out at JPL, basically as a gopher, and it was the best gopher job I ever had for the scientific teams there. And when we got the very first preliminary image that came back from the Neptune flyby, and you're just holding your breath because you're just waiting for to come in, and then it does when you're there. You're coming by the planet at closest approach, and there was just this wave of relief and cheering from all the scientists that came through. So I hope, and I'm looking forward to that coming true for Pluto.
As are we.
Yes, it's going to be a good feeling. And it's great to have you here and be getting a preview of what's to come in July. So please welcome John Spencer.
Thanks a lot, Andrea. Looks like the sound is working now? Yeah, okay. Thanks for coming tonight, and I'm going to tell you a little bit about what we know about Pluto, what we hope to find out with the New Horizons spacecraft that's going to get there in 105 days, not that we're counting, and we'll be sending back amazing data for our first ever close-up look at Pluto. We've never been near Pluto before, and it's an amazing place. And I'll try and give you some feel for what it's like working on the mission as well. So here goes. So just really basic stuff first. Where is Pluto? It's way out there. Here we are, close into the sun, with all our companion terrestrial planets in here. Then there's the asteroid belt, and we've got a big gap till you get out to Jupiter. And then we have to zoom out, and here's Jupiter, and bigger gaps out to Saturn and Uranus and Neptune. And then here's Pluto out beyond the orbit of Neptune, but not in a nice flat orbit like the other planets, but tilted, an orbit that's sometimes quite a lot closer to the sun than at other times. And you also see, and I'll say a bit more about this in a minute, that it's not the only thing out there. There's this whole swarm of other objects called the Kuiper belt out beyond Neptune as well, and Pluto is part of that newly explored part of the solar system. The reason we know Pluto is there at all is because of this guy, Clyde Tombaugh, who was hired by the Lowell Observatory in Flagstaff, Arizona, where I used to work. In fact, I used to live not in the house that he lived in, but a house built on the same basement. So I shared Clyde Tombaugh's basement, and I'm very, very proud of that. But anyway, he lived at the observatory too back in the 30s, and he was searching for objects beyond the known planets, Neptune being the most distant planet at that point, And he used this purpose-built telescope, which you can still see at Lowell Observatory. It has on the back here, not an eyepiece, but a big square box, a wooden box for photographic plates. And he would take long exposure photographs of the sky and take them several days apart and look for anything that was moving against the star background. And when you do that, mostly you see asteroids, but asteroids are much closer to the Earth and they move pretty fast. So he was looking for distant things that were moving slowly against the star background. And he would take pictures and develop them and then put them in this machine that allows you to look at two photographic plates on either side and flip between them. So you could see the stars fixed and then anything moving, jumping around. And he looked patiently for months and months and eventually came across this pair of images. And I don't know if you can see what Clyde Tombos are here, but it's not simple, so I'm going to make it a little easier. There. So there is the discovery pictures of Pluto. And this is a tiny fraction, maybe 1% of one of those photographic plates, and there were dozens of those photographic plates that he was going through. It's an incredibly patient job. And having found Pluto, he kept looking for another decade, because he found it pretty early just by dumb luck, and then continued to look at the rest of the sky and never found anything else out there beyond Neptune. But from this, we knew where Pluto was. We were able to determine its orbit, learned that it had this very surprising tilted orbit that was not circular, but was sometime much closer to the sun. And then we didn't learn very much more about Pluto for a long time. Here is a brief history of Pluto science. In the 1950s, we learned how fast it rotated, about every 6.4 days, which is pretty slow for a planet. And we found out why later. In 1977, we discovered there was methane ice on the surface of Pluto. That meant Pluto was pretty bright to have frozen methane on it, and that meant it had to be pretty small, much smaller than people had maybe thought before. In 1978, we found the big moon of Pluto called Charon, from which we could measure the mass of Pluto and determine that it was even smaller than we had thought previously. So that led in 1980 to a fairly famous spoof paper published in a respectable journal called The Pending Disappearance of Pluto, that it just seemed to be getting smaller and smaller and was rapidly going to disappear. But it stopped shrinking. It sort of stabilized at that point and is now, it's about 2/3 the size of our moon, about 1/5 the diameter of the Earth. And then since then we've steadily been learning more. We learned in 1988 that it has an atmosphere by watching it pass in front of a star and watching the dimming of the starlight as it went in front of the star. 1992, we discovered that Pluto is not alone out there beyond Neptune. We found the other objects in the Kuiper belt, which, or we started finding those. We found the first couple, but we knew there had to be, we rapidly realized there had to be hundreds of thousands of objects out there, most of them much, much smaller than Pluto. But Pluto was no longer just this oddball on the edge of the solar system, but it was part of this big family of other objects. 1993, we discovered nitrogen on the surface. And we assumed that therefore it was in the atmosphere as well. Got the first pictures from Hubble, which are still the best pictures, but not for much longer. And I'll show you those in a minute. Then in the last few years, we found other moons. It's got this one big moon, but then it has at least 4 small moons that we've discovered starting in 2005. The most recent was discovered in 2012. Nix, Hydra, Styx, and Kerberos is what we're calling those. So we've learned quite a lot about Pluto already before even going there with the spacecraft. This is a guess as to what Pluto might look like. This is what we've really got to go on here. This is the best picture we have, which is from the Hubble telescope, taken in the 1990s. And you can see there's some bright areas and some dark areas, and that's about it. But we do know from other stuff that some of those areas are very dark, and we think there may be some sort of tarry hydrocarbon gunk coating those very dark areas on the surface. And then other areas are extremely bright, and we think those are frozen nitrogen with methane and carbon dioxide and probably other ices as well. And, but until we get the real pictures, we have to make do with wild imaginings like this. This is the moon Charon. It's about half the size of Pluto, but very different. We already know that. This is, I shouldn't say this is the moon Charon. This is actually the moon Dione of Saturn. And I put it up here because it's about the same size as Charon, it's about the same brightness, it's about the same surface composition. So maybe Charon looks something like this, or maybe it looks totally different. We'll know pretty soon. But its surface is mostly made of water ice, which we don't see on Pluto at all. Just ordinary water ice like you find in your refrigerator, but also some ammonia and probably other things as well. And because Charon is so big compared to Pluto, Charon doesn't really orbit Pluto. They both orbit their center of gravity, and there's a little animation which I hope I can get to work here. And I may not get the animation to work, which isn't the worst thing. Oh, there it is. Okay. Yeah. Okay, so here we see an animation, and you see Pluto wobbling as Charon goes around it. Maybe click one more time to show it again. Yeah. So there's this very interesting dance between them. You'll notice that Pluto is always facing the same way side towards Charon. So they're rigidly locked to each other. And you could build a bridge between them if you were so inclined, because there's no motion between them. They're just rotating as though there was a bar connecting them, which is unique in the solar system. So yeah, with Hubble, we've got these great pictures. Well, not so great pictures, but the best we can get up to now. And then with long exposure pictures, we found these other moons. So here's Pluto and Charon, which are much brighter, but these little moons, Styx and Nix and Kerberos and Hydra, orbiting around quite a bit further away from Pluto than Charon does. And it's a very interesting system. It turns out Styx goes around goes once for every, I'll make sure I've got this right, once for every 3 orbits of Charon. Nix goes around Pluto for once for every 4 orbits of Charon. Kerberos goes around once every 5 orbits of Charon, and Hydra, you guessed it, goes around once for every 6 orbits of Charon. Pretty close. So there's some very interesting mathematical relationship between all these things that we don't understand yet. This is just, I won't bore you with all the numbers, but this gives you some idea of the sizes of these. They're, maybe 30 or 40 miles across, and the largest, these small moons. We think Charon was produced by a giant impact into Pluto early in Pluto's history that knocked off debris that coalesced into the big moon Charon and probably all these other little moons as well. And this is the same way we think the Earth's moon formed, that something very large, maybe the size of Mars, hit the Earth very early in the Earth's history and knocked off stuff into the Earth's orbit. So Pluto and Charon are the other example of this in the solar system, and we're going to be very interested to see what we can learn about how the Earth and the moon formed by looking at Pluto and Charon, because there might be some analogies there. So yeah, we know Pluto has an atmosphere. It's very thin. It's about 100,000th of the atmospheric pressure on the Earth. But like the air in this room, it's mostly nitrogen. There's no oxygen, though. There is methane and carbon monoxide, and probably argon and other things that we'll learn more about when we get there. It has probably some thin hazes, like shown in this artist's impression here, but we don't really know that at the moment. Here would be a Pluto weather forecast. It's pretty cold, and the winds. There are winds blowing that are transferring gas from the ice evaporates off the summer side or the day side and condenses on the night side, and there are winds blowing to do that. Barometer of 0.0003 inches of mercury. And the wind chill, you don't want to know about that. And you notice it's actually day for 3 Earth days and then night for 3 Earth nights because of this 6-day rotation period. So things happen fairly slowly on Pluto. And it doesn't actually cool off very much at night because the condensation of the frost at night actually keeps the surface warm. But yeah, not terribly hospitable. The nearest thing we have to decent pictures of Pluto are from, as Andrea was mentioning, the Voyager spacecraft that flew past Neptune in 1989, and when we were both there watching these pictures come in of Neptune's big moon Triton. Triton actually formed in orbit around the Sun, much the same as Pluto, we're fairly sure. It's about the same size as Pluto, has a similar composition, a similar density, and so they were probably basically siblings formed in the same part of the solar system, and somehow, we don't know how, Triton got captured into orbit around Neptune. And Triton, you can see, is a very weird and wonderful place with a multicolored surface and all kinds of exotic surface features that we don't even understand. Here's a close-up picture of part of Triton. And we're going to get pictures even better than this of Pluto in just a couple of months. And not only that, but we're going to measure the composition of the surface, do all kinds of things that Voyager could not do at Neptune, because we're dealing with a spacecraft with technology from 30 years more recent, and it's a much more high-tech spacecraft that is a lot more capable in many ways. And yeah, since 1992, as I mentioned, we've found that there are hundreds of thousands of other smaller objects out beyond Pluto, and a few big ones as well. So this is this Kuiper belt, and it completely dwarfs the asteroid belt, which is in here between Mars and Jupiter in the inner part of the solar system. There's probably 1,000 times more stuff out there than there is in the asteroid belt, but we didn't even know about it until 20 years ago, apart from Pluto itself. So now here are the other largest objects that we know about in the Kuiper belt. Here's Pluto and Charon, but here is Eris, which is pretty much exactly the same size as Pluto, has its own moon, but it's much, much further away, so it's much fainter. That's why we didn't know about it till recently. And other moons, Makemake, other objects, Makemake, Haumea, Sedna, Quaoar, and a whole host of others. And it's because Pluto has all these siblings that are similar or not that very much smaller that the controversy came up as to whether it was a planet or not, because there is no clear distinction between it and these smaller objects. And so it's hard to know where to draw the line, and it seems simpler to just reclassify it that way. But this is a third zone of the solar system. You have the terrestrial planets, you have the giant planets, and then the Kuiper belt beyond, where everything is very different. So shortly following the Neptune encounter, people started talking about it's really time we had a mission to Pluto to see what it's like up close. And so there were studies in the late 1980s and the 1990s. This is Clyde Tombaugh, who discovered Pluto in Las Cruces, New Mexico, where he lived the second half of his life, and his wife Patsy, talking to Rob Staley, who was one of the early studiers of missions to Pluto. So Clyde unfortunately did not live to see us actually launch a mission to his planet, but he was there for the initial planning stages, and he died about a year after this picture was taken. But some of his ashes are actually on the spacecraft. So part of him actually gets to visit the planet he discovered, which is kind of amazing. Oh yeah, so in 2001, NASA finally decided to put up the money to build this spacecraft to go to Pluto. And the way they did that is they invited anyone who had a good plan to say exactly how if they had the money to do it, exactly what they would do, what kind of spacecraft they would build, what kind of instruments they would put on it, how they would work out all those details, and said, whoever has the best plan, we'll give them $500 million to do this. And I was invited to participate in a team led by Alan Stern here, who is actually founded our institute here in Boulder, our branch of the Southwest Research Institute in Boulder. And we put together a proposal. This is the cover page. In October 2001, we had a NASA briefing, and all the bigwigs from NASA came, and we provided them all this information. We built a model of the spacecraft to impress them here. And this is about what it eventually looked like. It was just a cardboard model at this point, but now we have the real thing nearly at Pluto. There was a very detailed review, and a couple of other teams who also proposed got reviewed equally hard, and we must have answered their questions adequately, because we got this email in November 2001 that we had won the competition and that we were going to be the team that got to actually build the spacecraft and send it to Pluto, and that was pretty thrilling. And there were more bumps along the way after that, but basically we were up and running at this point. So then there was a lot of work to do to go from this cardboard model to something that would actually work and fly to Pluto, and this is just a glimpse at the kind of detail that you have to think about. These as a block diagram of all the different power systems and the electronic systems that have to be able to talk to each other. And also everything has to be redundant. This is integrated electronics module number 1, and this is an exact copy of it. So if anything fails on one side, you can swap in the other side. And so you can, if something goes wrong with the spacecraft, you can't go up and fix it. All you can do is make sure you have backups on the spacecraft so that you can swap those out and keep going. But so far, everything's working pretty well. We haven't had to use any of our backups. Yeah. So here are the instruments that are on board that will tell us about Pluto when we get there, and there's 5 or 6 of them, and I'll just go through them. Here, one of our prime instruments is MVIX, a multicolor visible imaging camera that takes wide-angle color pictures of the Pluto system. So we'll get pictures a little bit like this color picture of Triton here that was taken by Voyager. But it's a 5,000 pixel wide camera, so we'll get very detailed color pictures of Pluto with this camera. Then we have LORRI, is our long-range reconnaissance imager. This is like a pair of binoculars. It's a telephoto camera that can take much more detailed pictures, but only in black and white. And so this is an example of a close-up picture of Triton, the kind of level of detail that we'll see. That we'll see even more than this in just a couple of months when we get up close with this very powerful camera. We have an infrared spectrometer, which will tell us what the surface is made of. And it does this by dividing the light into many different wavelengths, like 200 different wavelengths of infrared light, and that contains all kinds of information of what the surface is like. And you end up with a bunch of squiggly lines like this, but these squiggly lines that show you how much light is reflected at different wavelengths have a fingerprint of the material the surface is made out of. And this might actually be Charon or one of Saturn's moons, but it's because of these dips and wiggles in the spectrum that tells us that this is made of water ice. And so we can make compositional maps of Pluto and Charon and the other moons as well. This is a very powerful instrument. We have an ultraviolet instrument that will tell us what the atmosphere is made of. We have plasma instruments that will see how fast Pluto's atmosphere is leaking into space. Pluto's very small, and its atmosphere extends a long way, and it's actually flowing continually away. So Pluto will have lost a lot of material over the edge of the solar system, and these plasma instruments will be able to feel that leaking of the atmosphere and tell us how much is actually escaping from Pluto. We actually have a radio transmitter that will not only talk to the Earth and send our data back, but we will pass radio waves through the atmosphere so that we can measure the density of the atmosphere with this instrument. And we have, on the back of the spacecraft, dust detectors that, as the spacecraft flies through the solar system, dust particles will hit these. They do hit these, and will measure how much dust is out there in the outer solar system. And this is built by students at the University of Colorado, which has been an amazing opportunity for a generation of students now to work on a real space mission like this. So in 2004, with all this design done and all these instruments spec'd out, we were actually able to start building it. When I say we, I mean the engineers, and I had nothing to do with this, but it was very impressive to see it taking shape. So here's just the bare bones shell of the spacecraft. Here it is in 2005 with more of the bits added, the big main dish that communicates with the Earth up on the top here. Here it is being tested. You can get a feel for the size of it here. It's really a small spacecraft. We like to say it's the size and shape of a grand piano. It has this big dish. And the spacecraft is spinning when it is during its cruise through space, and it has to be well balanced. So here they're testing the spin. To get the balance just right, they actually stuck a couple of Florida quarters on the inside to balance it. So they're off to Pluto as well. And then it got shipped down to Cape Canaveral in late 2005. Here they're unwrapping it from the static bag that protects it from static electricity during the journey. And again, you get a feel for what a small spacecraft this is. Here it is being put on top of its the third stage rocket that will take it out of Earth orbit. That's in the background here, nicely wrapped in all its gold insulation. And here it's been enclosed in the nose cone that will protect it on its ride out of the atmosphere. Here's Alan Stern, our leader, inside the nose cone just as they're closing up and about to close it down. I'm sure they had to drag him out of there. As it was pretty much, that was the last time people could really see the spacecraft before it was enclosed and ready to go. And here it is, sealed in the nose cone, early one morning, about to be hoisted onto the top of this huge rocket. This is an Atlas V rocket built actually in Colorado, down in Lockheed Martin's facility south of Denver. And this is one of the most powerful rockets that NASA currently has available. And you see we have this little tiny spacecraft. It's kind of silly how small this spacecraft is inside this huge rocket. But when you have a really big rocket and a really small thing that it's pushing, you go really fast. And so we're actually one of the we're the fastest launch ever from Earth. Here we did launch in January 2006, 36,000 miles an hour departing Earth. It only took 9 hours to pass the moon's orbit. And then it's 9 years at that speed to get to Pluto. Gives you an idea how big the solar system is. It was pretty thrilling to watch this go up, as you can imagine. Here we all are cheering it on. Here's me on the left here, it was quite the thing to see. And then we had a party afterwards, and the launch team got their trophies as thanks for getting it safely on its way. And then I like this bit. I guess this is a tradition after a successful rocket launch, is the burning of the contingency plans. So you have to have all this paperwork for what to do in case anything goes wrong at the launch. And once it's launched, you don't need those anymore, and they put them in a bin and burn them, and that was fun. And then we had only a year before we had our first part of call, which was Jupiter. So by 11 months after launch, that's wrong, that should be 13 months. I need to fix that slide. But anyway, just about a year after launch, we got all the way out to Jupiter. That's how fast we were going. And we used the gravity of Jupiter to give us a bit of a boost and cut a couple of years off our flight time to Pluto. And so here we are flying past the Jupiter system, fairly far out compared to most of the moons. Actually, this is where the moons were at closest approach, and it would have been nice to get a close-up look at the moons, but you see where all the moons were when we were at closest approach. They were all hiding from us on the other side. But we still got some nice pictures, and we were able to check out all our instruments and make sure everything was working smoothly. But it was quite a scramble to get ready for this because we had such a short time after launch to prepare for the encounter. But this is a picture of Jupiter taken with the LISA, the infrared instrument. So again, we can make one of those squiggly line plots, an infrared spectrum for pretty much every pixel in this image to tell you a lot about the clouds of Jupiter. That's kind of, and we'll get similar kind of data to this from Pluto itself. This is a picture from our wide-angle camera. We couldn't take all the pictures we would have liked at Jupiter because it's so bright at Jupiter. We have a camera that's designed to work in the dim outer reaches of the solar system where there's not very much light. So at Jupiter, the sun is so bright, we're so close to the sun, even though it's 5 times further than the Earth, that a lot of our pictures we knew were going to be overexposed. But we got some that were pretty good, and this is an example that you can zoom in on little details here and get some feel for the level of detail that we have in these pictures. One of my favorite places in the solar system is Jupiter's moon Io, and this is a view of it with some of our instruments. So the LORRI camera got the sharpest images, but they're in black and white. These are erupting volcanoes. This is the glow of lava from an erupting volcano on Io. And this is a big canopy of debris being thrown out by that volcano. Our color camera, the images aren't as detailed, but you can see the red glow of that volcano and the blue color of the very faint smoke-like stuff being ejected from that volcano. And then the infrared instrument is seeing the glow of a dozen other volcanoes on the night side of Io. They're putting out infrared light that we can detect there. So we really have a powerful set of instruments here. We can look at the system in all kinds of different ways. We even got a movie, and so if you can click on that image, I think we should see a movie of those. And if we don't, it's not that big a deal. Anyway, but it was really cool. Trust me, that you could actually see this volcano. You could see the material flowing down that canopy. It doesn't matter that much. It's just kind of a cool picture. No? Oh well, that's all right. It's really hard to get movies to work in PowerPoint presentations. But anyway, no one had taken a movie of an extraterrestrial volcano before, so we were pretty proud of that. And we took some pictures just because they were scenic. This is a picture of Io with its erupting volcanoes, and there's the red glow of that volcano again, of the red lava there. And then this is the moon Europa that just happened to be passing by it at that point. Europa is also an amazing place. It has an icy surface that we think has a massive ocean underneath the ice. And NASA is very interested in sending a spacecraft back to look at Europa in a lot more detail. So maybe in 15 years or so, we'll have a spacecraft investigating Europa as well up close. Here's Europa just setting behind Jupiter. Not the kind of thing you see every day, but it's a really spectacular place. And then we were in for the long haul. Here's the Earth 2006, Jupiter 2007, Pluto 2015. So we have an 8-year cruise from Jupiter out to Pluto, where we didn't really pass anywhere else in the solar system. But we managed to keep pretty busy. But every year we'd have a cake for the spacecraft at launch. So this is the 3rd anniversary of launch. Here's the 6th anniversary of launch. And some of the team members here in our Boulder office. But we were also very busy during that time because we had a lot of work to do to figure out exactly what to do when we got to Pluto. We fly past the Pluto system in a matter of a few hours. It takes 4.5 hours at the speed of light for any instructions from the Earth to get to the spacecraft. And it takes 4.5 hours for any acknowledgement from the spacecraft to get back to Earth. So we have a 9-hour lag, which means by the time you can react to anything, you're already past Pluto. So everything has to be pre-programmed. Everything has to be built into the spacecraft sequence, sent up. In fact, it's been rehearsed. We came up with a whole sequence of exactly where we're going to point the cameras, all the other measurements we're going to make. And then we rehearsed the whole thing on the spacecraft 2 years ago. And the spacecraft went through all these maneuvers and took pictures of nothing. And everything worked smoothly. So we know exactly what we're going to do when we get there. But to get to that point was an enormous amount of work, just figuring out all the ways to use our instruments most effectively in that very precious couple of hours that we're close to Pluto. We have a large data recorder. It's, I think, about 100 gigabits, I think, that we're just going to fill up with images, and then we're going to take months, up to a year, to send all that information back. So we just take data like crazy, all in this pre-programmed way, trying to anticipate everything we might want to find, even though we can't react in real time, and all kinds of contingencies. So if something goes wrong with the spacecraft, it will be able to pick up where it left off and carry on and maybe get the same kind of information in some other way. So this was a lot of work, and here's some of the high-tech equipment we used for designing some of the observations. Lots of cups of coffee and staring at computer screens trying to figure all this out. Here is just an example of, there end up being hundreds and hundreds of spreadsheets. That seems to be how a lot of stuff gets done. This is sort of an overview of the things that are happening in June. Here's one column for every day of the month of June. And these are all the different kinds of observations we make and how many we make every day. And this is just the top level of detail of the plans. Here's a detailed line, one line for every activity that the spacecraft does for just a couple of days, switching on heaters, turning at various rates to different targets, turning back to the Earth to radio the information back. All of this has to be worked out, and we're still putting the finishing touches on this. As we're approaching Pluto, we figured out what we're going to do when we're close to Pluto several years ago, but the last stages of the approach, we're pretty much planning in real time, so we will figure out a couple of weeks worth of data. We'll review that. That'll be sent up to the spacecraft. And we just do that 2 weeks at a time. And so we're nearly finished with that process, and we'll be very happy to be done with that planning, and then we can start paying a full attention to what's coming back from the spacecraft. This is, if you were to look down on the spacecraft's trajectory past Pluto, here is Pluto, and there is the moon Charon. We actually pass by on the side opposite from Charon. And then we pass through the shadow of Pluto back here. The sun is over on this side. We're coming from that direction. We pass through Pluto's shadow, then we pass through Charon's shadow later on. And then each of these colored bars is a different activity that we're doing as we fly past. So the red ones are infrared scans to measure the composition of the surface. The gray ones are black and white, high-resolution pictures from the LORRI instrument. Blue is ultraviolet, and the green are our color pictures, and so on. And so we have this very tight sequence of events, one after the other, as we go past to make the most of the encounter. Yeah, absolutely.
So you were talking early on that the spacecraft is spinning. Mm-hmm. Are you going to stop the spinning?
Oh, yeah.
As you're passing by?
Yeah, as it's in cruise on those 9 years, it's mostly spinning. And it's mostly asleep. We've had it in hibernation most of the way, where most of the system shut down. That saves wear and tear on the instruments. Once a year, we wake it up and we do some tests of check the calibration of the cameras, make sure everything is working okay. Then we put it back to bed for another year. But while it's in hibernation, it actually sends a signal, just a brief signal back to the Earth once a week saying, I'm fine. And occasionally we get a signal saying, I'm not fine, there's a problem, and then we have to wake it up and see what the problem is. And it's never been anything very serious. There's been some little computer glitches that we've had to deal with. But as of, I think it was late December, just before Christmas last year, it came out of spin mode and is now mostly pointing is stable in whatever direction we want it to point, and that's how we can start taking pictures and things. We actually spun it up again in March, because when it's spinning we can send more data back. So we accumulated a bunch of data on the spacecraft, then we spin it up, send that back, and now we've spun it down again just last week, or is it 2 weeks ago? And that was cool because we'd had a gap of about a month when we hadn't taken pictures. So suddenly the pictures we're getting now are quite a bit better than what we were getting a month earlier. So we get this sudden leap in the quality of the data we're getting from the spacecraft. And we'll do that again one more time. In late May, we spin it up and we send back the data. And after that, it's going to be full-time on the job in what we call 3-axis stable mode, stationary, but pointing whatever direction we need it to go. And so through this entire period, it's not spinning. So this is where we were as of yesterday. This was yesterday's slide, but we're almost there. Not very far to go to Pluto at all. Probably, well, let's see, distance from Pluto, that's about 60 million miles, something like that. Closing in about 600,000 miles a day, something like that. In time for our appointment in July. We're still making little adjustments to the spacecraft trajectory. We're taking pictures of Pluto against the background stars. We're measuring its exact location with radio telescopes, and every couple of months we say, oh, we need to nudge it a little bit to make sure we arrive at the right place at the right time. And so we've done that a couple of times. We'll do it a couple of times more. But everything is going very smoothly. And of course, we've already started getting pictures. Back in July 2013, we got the first pictures that showed Pluto and its moon Charon separately, and there they are. We were pretty excited at that point that we could actually just see the big moon Charon separate from Pluto. It wasn't just a point of light which had been up to that point. A year later, July 2014, only a year to go, then we could very clearly see Pluto and Charon separate here, and we actually had a movie of them going around each other. And this I thought was kind of fun. This is just a picture of the star field taken in July 2013. And one of those is Pluto, and there's no way to tell which it is, except when I show you the picture taken in 2014. Now you can tell which is Pluto against that star background. It's moving, it's getting brighter, and now it's even brighter. It's probably 10 times brighter than this by now. We still see the same stars in the background because we're heading pretty much straight for it. This is pictures taken in January this year. You might try clicking on that, see, because that is, I think, supposed to be a movie. You can see Charon going around Pluto, but it might not work, and it's not that big a deal if it doesn't. Now that's okay, not to worry about it. But we now have a series of pictures where we see Charon going around, and if you go to the website, I'll give you the web address at the end. You can actually see these movies, and we'll be releasing more stuff as we get closer. Now we're getting close enough that Pluto is starting to show a disk. You can't see much on it yet, but you can start to see it's not just a point of light anymore. And so pretty soon we'll be seeing detail on the surface, and then it's just going to get better and better pretty much every day after that. This is, oh, this one, it does actually work. These are the two moons, Nix and Hydra, as well as those images to show Pluto and Charon. We're taking long exposure pictures where Pluto is totally overexposed, and it's just this fuzzy blob here, and there's electronic effects because it's just so overexposed, and we see all the stars in the background. But here are the moons, Nix and Hydra, the brightest of the two additional moons, orbiting around Pluto just as we expect them to. And these are the same images, but here we've worked very hard to remove all the stars and remove as much of the glare from Pluto as we can. So we can see Nix and Hydra. And we haven't seen the remaining two moons yet, Styx and Kerberos. This weekend, I'm going to sit down with my computer and I'm going to try really hard to find Kerberos. We now have enough pictures that are close enough that I think if we work really hard, we might be able to pull it out. And seeing each one of these objects as we approach, it's like seeing a familiar landmark that we know that, and we know we're nearly there, and each one is an important milestone along the way. So I'm very much looking forward to picking up Kerberos. And then Styx is fainter. We probably won't see that till next month. Last week we got the first color pictures. We turned on the color camera for the first time. We're now close enough we can get color pictures. It's a horrible picture by any standards other than being really cool to be the first color picture from close up to Pluto. This is not the actual size of Pluto. It's just kind of blurred out here. They are different colors, but it's very hard to see the color difference in this picture. We actually went to a lot of work to try and see if we could bring out that color difference, and we're just too far away at this point to see that clearly. But Pluto is a little bit browner in reality, and Charon's a little bit grayer, and soon as the pictures get better and better, you should be able to see that. Right now they're just fuzzy blobs, but we're very excited to see those fuzzy blobs with our color camera now. So by May or early June, we should get better than this picture I keep showing you, because it's the best we've got. We're going to start doing better than that. We're going to be seeing details that have not been seen up to now at all. And after that, every day we'll be seeing stuff that has never been seen before as we get closer and closer. And then something that I'm working on has taken a lot of my time, and I was out at Mission Control in Maryland last week practicing, is that as we approach Pluto, we're taking long exposure images to see if there's anything dangerous in the way of the spacecraft's path. We're just to see if the coast ahead is clear, and we're the guys in the crow's nest looking out for reefs ahead. If we do see anything on the spacecraft path, which we certainly don't expect to, then we can take evasive action. We can actually change the spacecraft to another trajectory that might avoid any rings of dust or anything that might be hazardous to it. We don't expect to have to do that, but we'll be ready if we do.
Yeah. Any interesting dust?
We haven't seen anything yet. Oh, the dust detector is detecting dust out through the solar system, and they are finding more dust the further out we get, if I remember right. Which means we're approaching a dusty part of the solar system. The Kuiper belt is generating dust, and so we're starting to pick that up as we get out towards that part of the solar system. But anything we detect with that detector, it's going to be too late by the time we see it, because we'll be right in amongst it and it'll be too late to do anything about it. So any dust that we want to avoid, we have to see with our cameras from long distance on approach. So we'll be doing that, and that's going to keep me busy over the next few months, is working on that effort. These are not real images, but this is an example of how we do this. This is a simulated image taken, that this would be just about 3 weeks before we got there. Pluto and Charon will be very bright, and there'll be ghosts in the images and these kind of electronic artifacts. But by taking pictures a couple of hours apart, can you see the moons orbiting around? Not just the big moon Charon, but the little moons, a couple of real ones and a whole bunch of imaginary ones I put in this picture just to see how well we could see moons. But this is the kind of data we'll be working with to try and see if there's anything else out there. Hopefully we'll see some new moons. We're looking forward to finding new moons, but we're looking forward to them not being in the way of the spacecraft. And we'll see how that goes. And then 3 days out, we get our best view of the far side of Pluto. These are a series of images that are what it would be like if instead of flying past Pluto, we were flying past our own moon, so you can get a feel for the quality of the data. So these are about the best pictures we will get of the far side of Pluto, though it's really the far side of the moon here. And you'll see, we actually see quite a lot of detail on that side. But then, because Pluto takes 6 days to rotate, as we approach closer, this side rotates away, and we start to see the opposite side in more and more detail. About a day before we get there, this is the best pictures we'll have. You're starting to see a lot of detail now. And the best pictures we will get down from the spacecraft before the flyby, will be on July 13th, the day before we get there. We'll have a picture down like this, and we will be releasing those, and so we'll have this as our best pictures before we get there. We've actually been doing rehearsals that we're calling the New York Times Operational Readiness Test, where we're figuring out what to do with these images. When we get them down, we need to process them, figure out what's in them, write press releases, get them out so they can be hopefully on the cover of the New York Times the next day. And so we're not only doing science, but we're making sure we can get stuff out to the public as quickly as we possibly can. So we'll very much look forward to these pictures. And then the day of the closest approach, we don't actually get much information from the spacecraft because it's working really, really hard collecting data, and it's not going to be phoning home very much. But I'll go on and just take you through the encounter day. This is 12 hours out. We'll be getting this kind of level of detail, seeing all kinds of fine details on the surface of Pluto. I'm sure it will look nothing like this, but it's going to be amazing. 3 hours out, we can no longer fit it in a single photograph. We have to take a mosaic of, this is 12 pictures, I think, 16 pictures to cover the whole of Pluto's disk. Each one of these is a bunch of overlapping squares. About that same time, we'll be scanning the surface, getting these multicolor images of the composition with our infrared instrument. This happens to be Mercury, but it gives you an idea of the kind of detail we'll be seeing in that. An hour before closest approach, now each frame of our camera is just covering a tiny part of Pluto, and we can't even cover the whole thing with our cameras in the time we have available, but we'll get samples of areas at high resolution. 40 minutes out with our wide-angle camera, it's going to fill our wide-angle camera. We'll get pictures, 5,000 pictures across, 5,000 pixels across, this kind of level of detail over the whole of the disk, and that's just going to be spectacular. Closest approach, we scan, again, each of these red squares is a full picture from our narrow angle camera, and we'll get 20 of them, 20,000 pixels from the horizon to the edge of the nighttime here. It's just going to be incredible. And at the same time, this blue square is a swath that we will cover with our wide angle camera. We won't even be able to fit the whole of Pluto in our wide angle camera then. Our closest approach is 12,000 kilometers from the surface. And so Pluto will be about this big in the sky. It's going to be quite an impressive sight from the spacecraft. And then we pass behind. We actually watch the sunset behind Pluto. With our ultraviolet instrument, we measure the sunlight passing through the atmosphere to learn what the atmosphere is made out of. And then we recede from Pluto. We take images of the receding crescent for a couple of weeks. And then we get into the business of sending the data down. And it's going to take us about a year to get all the data down. It won't be till late 2016. So every day is going to be Christmas Day. We'll have some new goodies down from the spacecraft to see. We'll learn something new pretty much every day for all that time. It's going to be quite something. But then we keep going. And I've mentioned the Kuiper Belt a couple of times, this area out beyond Pluto, which has hundreds of thousands of objects. Pluto will not be our last port of call, or we hope it will not be our last port of call. We want to fly past another of these objects out there, nothing as big as Pluto, but one of these hundreds of thousands of much smaller objects that are much more typical. So to do that, even though there's 100,000, that's an extrapolation from the few that we actually know about. We didn't know about any that were along the path of the spacecraft. It looks like here they're so dense that you could hardly avoid hitting one, but in fact space is so huge and empty that it was actually pretty hard to find an object that we could reach that was close enough to our trajectory. We've used these big telescopes in Chile and Hawaii, taken 4 years searching the sky in the region we need to look at, where we knew anything would be if we could reach it from the spacecraft. One thing that made this really hard is just by bad luck, the area we have to search is right in Sagittarius. And if you know the sky and you know the star clouds of Sagittarius, you know you don't want to be looking for tiny 27th magnitude faint moving objects against the millions of stars in that part of the sky. And that's made this job really difficult. And we actually found about 60 Kuiper Belt objects out there beyond Pluto in the right part of the sky, but just none of them were quite close enough to the spacecraft trajectory to reach with the amount of fuel that we had. So last year we turned to the most powerful telescope we had available, and again this was the Hubble telescope. We got about 1,000 pictures from Hubble. It was a big investment of time by the telescope. And we found 2 objects that we can actually reach. This is a picture of one of them. Again, it's helpfully got a green circle around it. You can see in this, we're just looping the movie, so it seems to be moving backwards and forwards against the background stars. So you see it's really faint compared to all the other things in the images, but we had some amazing people working on this, some of whom are shown in this picture. It was a pretty intense time. Every day we were getting new pictures down from Hubble. First of all, we made a deal with them just to show that we could do this. They said, give us 20% of our time, and if we can't find at least 2 objects, whether we can reach them or not, in those images, you don't have to give us the rest of the time. So the pressure was really on us to actually find something, and we had to find it very quickly in time to get the rest of the time. So every day we were meeting, and this is one of our daily meetings, going through the data. And with about a week to spare, we found two objects. This was one of them. And that allowed us to get all the rest of the data, and then we found 3 more. And out of all those objects, we have 2 that we can actually reach with the spacecraft. We have enough fuel to get to them. And now we have to choose between them. This is where they are. So here again is the spacecraft path, and here's the Earth and the asteroid belt. This is our puny little asteroid belt between Mars and Jupiter. And then here's the Kuiper Belt, this huge space out here. This is a pretty accurate depiction of where all these objects are. Here's our trajectory. And here are these 2 guys. When this graphic was done, they were just called potential target 1 and potential target 3. It turned out we couldn't reach potential target 2. Now they have these official, not really names, but more like license plates. we'll be holding a competition for names for these objects at some point, but right now they just have these rather ungainly names. And one of them, let's see, I think this one is easy to reach. We'll have lots of fuel left over, but is a little bit fainter. This one is harder to reach, but is brighter. So it's not an easy choice between them. And we have to decide by August, because in October, we're going to fire our engines and set a course to one or the other of them. So we have to make that decision fairly soon. And then in late 2018 or early 2019, we're going to fly by one of these. If we get approved by NASA, I have to remember to say that, because we will not be, we do not have funding for this part of the mission yet. We have to set our course, and then we have to ask NASA for the money to do it. But we can't afford to wait for the money to set the course of the spacecraft. So we'll be going through a process next year of telling them what we want to do, and hopefully getting the additional money, the small amount of additional money we need to fly that part of the mission out into the Kuiper Belt and see what these other objects are like. Yeah?
You say close, how close?
We haven't decided yet, but it'll be probably about 10 or 20,000 kilometers, something like that. We haven't decided yet. We can decide that later. But again, we have to decide it many months in advance so we can send up the sequences to the spacecraft and target it to the right location and everything. So still lots of work to do. It's going to keep us busy for quite a bit longer. And then we just keep going. We're going out into interstellar space. There's nothing to slow this spacecraft down, no friction to slow it down. It's going at much greater than escape velocity from the sun. And we're going to keep in touch with it probably into the 2030s if we are funded to do that. But at that point, the power supply will have dropped to the level that we can really no longer power the instruments, and it'll be too far away to talk to the Earth, and we'll have to stop talking to it at that point, but it's going to keep on going and having its own adventures out into the galaxy. And so we've got quite a wild ride ahead of us. And I think that's the last slide, except to bring up the website that you can Google New Horizons or Pluto and find it easily enough. But this is where we're putting all the goodies and lots of more information on the mission there. And that's my talk. And yes, I'm very happy to answer questions at this point. So yeah, at the back.
Can you back up 2 slides?
Sure.
2 slides to your Kuiper Belt.
Yep.
So do you have any references to just which direction the Voyager spacecraft are heading in? Compared to where we're going?
I think they're heading in the same general direction, but Voyager 2 flew past Neptune when Neptune was about here. It actually went in a very similar direction. We went past Neptune's orbit actually 25 years to the day after Voyager reached Neptune, we passed Neptune's orbit. It's just a cool coincidence. And we took a picture of Neptune at that time, except Neptune was way over here by then, so it wasn't anywhere near the spacecraft. But Voyager, when it flew past Neptune, Voyager 2, it flew over Neptune's pole and that deflected it down, so it was kind of going in this direction down. And I think Voyager 2 is going up, having flown past Saturn, and it's going up this way. So they're all on the same side of the solar system, but going in quite different directions. And Voyager 1 is going the fastest and is the furthest out. And so as you may have heard, Voyager 1 has now in interstellar space. It's past the edge of the solar wind, and we'll be following and hoping to do the same. Yeah. Oh, yeah, go ahead.
Is your briefing available online?
Say as a PDF.
This talk, no, but apparently it's going to go on YouTube, and
YouTube within about a week.
yeah. So you can find all the mistakes I made at your leisure later.
How
Yeah.
long will it be before you pass Voyager as being the farthest man-made object?
We actually don't, because even though we launched faster than the Voyagers, they made close flybys of Jupiter and Saturn, and then Voyager 2 went past Uranus and Neptune, and they picked up speed every time. they went past one of those planets. So now they're going faster than we are, even though they started out going slower. So we won't catch up, but we'll give them a run for their money. Yeah.
Talking about your spacecraft and what's equipped with, what do you use for power supply for batteries and so on?
We're actually using plutonium as our power supply. It's kind of cool that we're sending plutonium to Pluto. It's plutonium-238, which is not weapons-grade plutonium. It's a different isotope, but it's very radioactive, such that if you had a chunk of plutonium and you put it into a dark room, you would be able to see it glow, not from radioactivity, just because it gets so hot from the energy released by the radioactivity that it glows. And so we have a thermocouple that turns that heat into electricity, and that's what powers the spacecraft. And that is gradually declining as the plutonium decays, but it's got plenty of power to power us for Pluto and for a decade or two beyond that. Yeah, the back there.
What is total program cost roughly?
It's about $730 million, which is pretty cheap for an outer planet mission. The Voyager spacecraft would be several $billion in today's money, and the Cassini spacecraft that's orbiting Saturn is much more expensive than New Horizons. So it's quite the bargain to see a whole new world, I think. Yeah.
Did you use radiation-hardened chips?
Oh yeah. We can't use the latest state-of-the-art electronics that you might have in your phone, because everything has to be absolutely rock-solid reliable for a long space mission, which means there has to be a lot of experience with it. Preferably it's flown before, maybe in Earth orbit, and we know that these are things that will withstand the fairly harsh radiation environment in space. So yeah, it's not just off-the-shelf electronics. Yeah?
Did I get this right? You got approval in 2001 and you were building by 2004.
Mm-hmm.
How did you do that in such a short amount of time?
It was quite the operation. Yeah, we had a fairly short fuse, because by the time NASA decided that to fund the mission, we wanted to have that Jupiter flyby to get the boost to Pluto, and that only left 3 or 4 years. And so it was really a pretty fast track to get the spacecraft built. And yes, we just had a really amazing team at the Applied Physics Laboratory in Columbia, Maryland, who put this together, and also had to get the launch approval for the nuclear launch. That took most of that time, and there were some people who were skeptical as to whether it could be done in time, but we convinced NASA in advance, and then we were actually able to do it with some time to spare.
Just to follow up, were all these instruments custom built, or was some of this off the shelf?
No, the instruments were all custom built. Some of those have been designed years earlier. I started working on this 20 years ago with a small team led by Alan Stern again, who were at that time just designing cameras for the spacecraft. But the camera that we're actually flying, our wide-angle color camera, MVIC, is very similar to what we were designing 20 years ago. So we had a leg up on some of the designs before that 2001 opportunity.
So I walked and went late, I apologize. Were you able to get the color picture from Ralph up there today?
Yeah, I can. If I can go back there, I can show you the color picture that we released last week. There. It's unimpressive, but it's our first color picture. We're very excited. And again, this is the camera that we were designing at Boulder. Actually, this camera was built at Ball Aerospace in Boulder. That's another Boulder connection with this.
On our website, I work at Ball, so
oh, okay.
Website this morning.
Yeah, and so 20 years ago we were designing this, and now finally it's doing what it was designed for at Pluto, or very close to it now, and it was pretty thrilling to see these pictures, even though they don't look like much yet, but you ain't seen nothing yet.
That's from 60 million miles, though.
Yeah.
That's pretty good.
Yeah. And it's a wide-angle camera. It's, you know, it's not designed to get the high resolution like the Lorry instrument. But yeah, we'll start seeing details with that soon enough. If any more questions? If not, I'll hang around a little afterwards if you want to ask me. Oh, yeah.
Could you just go to the last slide that had your website?
Oh, sure. I mean, you can probably find it by Google easily enough, but there it is. And yeah, we'll be keeping that up to date with all kinds of goodies. Yeah?
So besides the website, are you keeping up to date on the Facebook page or any other social media?
Yeah, I'm too old to keep up with the social media stuff, but we have, I guess the link isn't here, but if you scroll down, there's a Twitter feed and there's a Facebook page and all that stuff. So we're using everything we can think of to let people know what's going on here. At the Encounter, there will be an event at the Fisk Planetarium at University of Colorado, a Pluto Palooza, and you'll be able to see the pictures and see us all waiting with bated breath for that first confirmation after closest approach that will tell us the spacecraft made it through the system safely, that we will all be very much looking forward to seeing.
So, of the two objects that you get to choose from in the next couple of months, do you have a personal preference?
I would like to go to the bigger one. It's about maybe 50% bigger, something like that. It's not a huge difference, but we'll get more data from the bigger object. So we're now just figuring out, do we really have enough fuel to get there and still have enough fuel for everything else we want to do? So we have to do a pretty thorough vetting of all the things that might require fuel, and that means thinking quite hard about how we do the navigation as we approach it and so on. And at the same time as we're doing that, of course, we actually have a Pluto encounter to fly. So we've got our work cut out for us. So I'm hoping we can go to the bigger one, but it's by no means certain yet. We're very lucky. The other one, it requires, for a while it seemed like there was some tiny chance we might actually run into it. It was so close to our direct path that it really will leave us lots of fuel to spare, and we can probably target that one with confidence. And again, this will all depend on getting money from NASA once we are on our way. Yeah.
Is it the job you're going to retire on, John?
Sorry?
Is it the job you are going to retire on?
Well, we'll see. I hope to have a few years left in me after the KBO flyby. After that, it'll be the mission will be mostly for the plasma people who will be measuring the solar wind and as we go out towards the edge of the sun's influence, and it will be of less interest to me by that time. But yeah, it's going to keep us going for a few years yet, we hope.
What is the fuel?
Well, so the power supply is plutonium. The fuel that it uses to change its trajectory is hydrazine, and that is allows us to not only change our course, so we'll set a course to the whatever Kuiper belt object we choose, but it's also, we have little thrusters which we use to change our orientation. And so that's how every time we point at something new, we're using up a tiny amount of our fuel, so we have to budget that as well. So all these things get interconnected in interesting ways. Yeah?
Why did you decide not to put it into orbit, or could you?
Oh, we didn't have that option because we're going very fast. In order to get there before we die, we have to go pretty fast. And even then it took 9 years. And you saw that huge rocket that it took to get us up to that speed. We wouldn't need a rocket quite that big to slow us down, but we needed something pretty darn big to slow us down, kill all that speed again to get into orbit. And it's a small lightweight spacecraft. If we waited to have a rocket to do that, we would not be flying to Pluto because we wouldn't be able to afford that big of a spacecraft with that big of a rocket. So, and it's nice because having this allows us to continue exploring beyond Pluto, of course, but even if we'd wanted to stay and look, we'll have to wait for the next generation of astronomers and the next generation of technology to go into orbit. Hopefully we'll find such cool stuff that we're really going to want to go back and stay for a while and get a closer look. I'm sure we will. Yeah?
You showed a kind of a landscape, hypothetical landscape of Pluto before the sun in the distance.
Mm-hmm.
Is that not the actual brightness, or is that enhanced?
The brightness of the sun or of the landscape? It's hard to really compare because it depends what you're used to. The lighting in this room now is probably not too different from ambient light on Pluto. The human eye is incredibly adaptable to huge ranges in brightness, and you can walk around in moonlight and see where you're going, and that's 1,000,000 times fainter than sunlight. And Pluto is sort of somewhere in between. And I think just normal indoor evening room lighting is about the brightness of full sunlight on Pluto. So you'll be able to see colors, read a newspaper or whatever there, and it's not as dim as you might think, just because the eye is so adaptable. But it's still 1,000 times dimmer than full sunlight, and as is the light in this room.
Well, unfortunately, it's all clouded over again.
Ah.
We came in, it was nice and clear, and everything is beautiful right now. We have a solid overcast, so no telescope viewing probably.
Yeah.
We'll still give you a little tour of the telescopes, but
Yeah.
no viewing, I'm afraid, tonight.
Yeah.
Let's give John another round of applause.
Thank you. And thank you all for coming, and thanks for the invitation and for the great questions.